Let's say you went to sleep tonight and you were sound asleep. Imagine that everything in this universe became 1,000 times larger or 1,000 times smaller. And by everything, I mean electrons, atoms, me, you, the sun, the stars, everything. Now, when you wake up to this new world, will you be able to make out the change? These might seem funny, but useless thought experiments. Until Noether gave us one of the most beautiful, profound, and grand ideas of all physics and mathematical history. To all those inquisitive minds out there, I give you the Noether's theorem. Now, consider the symmetry of yourself looking into the mirror. When you move your right hand, there is a corresponding movement in the mirror. Similarly with the left hand. Now, the movement in these two realities is such that there is no difference between them. Noether pointed out just that. She said that if the system we live in is symmetric, then random motions can be studied under conservation laws derived from these symmetries. Now, if I were to drop the ball here, the laws of physics would remain the same if I were to drop the ball from here. Mathematically, if there is a system and you perform a transformation, and if the system still remains the same, then it is said to be symmetric. But not all systems are symmetric. If I were to drop the ball standing on the ground, it would have lesser gravitational potential when compared to the fall from the top of the tree. There is no translational symmetry involved here. Hence, the momentum is not conserved. Now let's bring in some rotation. So this wheel rotating here wants to rotate in the same direction. So when I try to change the direction, there is an opposing force created, or a torque created. Now why does this happen? This is to conserve angular momentum in rotational symmetry. Energy is neither created nor destroyed. Then what is the corresponding symmetry that we observe in nature? I guess it's time to take a break. Wait a second. Time. There is no change in the laws of physics at the times of Newton a few centuries ago till now. Hence, we live in a reality where space and time are symmetric. The deep connection between symmetry and conservation laws require the existence of the principle of least action. Now, if you were to race down your friends from school to Harvard School, which among the two world lines would you think will take you faster to Harvard? The product of the Lagrangian and time gives us a quantity called the action, which is less for the curved path when compared to the straight line. Nature works in a way to minimize this change of action, giving us the least change in the latent energy of the system, called Lagrangian under the curved path. Now, if the latent energy, or the Lagrangian, in a given system remains the same, somehow, under any random change, then the system has just conceived a corresponding law of conservation. The theorem states that if the Lagrangian of a system is invariant under continuous transformation, then there exists conservation law. The usual summary is symmetry implies conservation laws. From our everyday experiences to quantum mechanics, to the general theory of relativity, to the supersymmetric standard model, to explaining the mass of particles, we use symmetry principles to extensively explore new frontiers in physical theory. Today, we realize that symmetry principles are even more powerful and they dictate the forms of the laws of nature. In our search for new and ever more fundamental laws of nature, we will begin our quest in search for new symmetries.